Hello, Professor and TA. I am Boyi Zhang. Uh, my project is about using cuda and opencv to implement a image denoising algorithm, which use total variation method. First of all, the introduction. There are many image denoising algorithms, from the stimulus convolution to Wiener filter, loss regression, and then to the current, which is really famous deep learning neural networks. The reduction problem can be solved better and better. And one algorithm which I was really impressed is about the total variation, since it's beautiful assumption and solution ideas. Then let's go to the algorithm. First of all, our algorithm has a limited gradient descent, which means we cannot to keep minimize the gradient because it will have some problem. First of all, if you make the gradient really small, this means your image will be very dark, since the smaller the pixel value is, the smaller the difference between the pixel value will naturally be. Second is about the if you minimize the gradient without a constraint, your image information will be disappear. This means that if you make the difference between image pixels to be very small, the whole image will be flat and it will like a mask, not like an image. Therefore, for the two problems, we need to constrain the gradient minimums, which are written out as this. Where the ux donates the gradient in the horizontal direction, uy donates the gradient in the vertical direction, u0 donates the original noise image, and double integration nodes of the sum. Here is the sum of the pixels all of the image. Then we are going to the Euler and Lagrange equation. We use Lagrange method to solve the problem, which we construct the equation like this. And we found that the root in the dual integral is a function such like this. And since L is a function about function, and it's difficult to solve, but fortunately the Newton gave a general formula for the general function minimum in his study, which minimum part of L satisfy us this. And in order to solve that, we need L is an integral form which represents as this, which is the true gradient of generalized function. But this is still hard to solve, so we need to make this more easily to solve. First of all, we use gradient descent in the general function represent this, but we don't care about the self-variant I, so it's like the EM algorithm. We need to compute like this, which can get the thing which we will need later in the program. This, and before all the formal math, we get the final gradient as this algorithm, which can be represented as this. This is what we will going to do in the future program, where the tx ulj is a nearly pixel decrease. The pixel decreased by the nearly pixel, and ty uij is also the same. It's the same of the equation. Finally, over the math part, okay, let's go about the program implement. Okay, first off, the main function is very easy, and use opencv to read image makes the image becomes a grayscale and make it to the from 0 to 1 to compute later. Then cuda malloc of the variable we need. Then cuda mem copy from the host to device and develop and make the grid, which is your image width divided by the phrase, and the block is the phrase multiplied phrase. And this is pretty important for the phase 4 loop, but we will discuss later. At last, we use the result to back to the host when we could free them out. Okay, to avoid the very many conclusion, we will use the calculation step into many intermediate steps, which includes this intermediate step in the function, which clear the variable we need in the for loop or the later. Okay, when the u0 is the original value of the image, u is the current value of the current iteration value, u temp is the intermediate result which will transfer to the next u. ux and uy represent the gradient of the in the x direction or y direction. ud is the gradient of the whole image, and ux1 and uxy1 is the gradient that we need to compute in the here. Yeah. Okay, then the for loop. This is a very important part. Basically, this is five line is a 5 step in the later. The cal uxy is used to compute txu, tyu, which is a function, which the implementation is here. We have here you say ux, uy, and u to get the u. And then cal ud use the ux, uy to which work. Oh, sorry. It's use u to compute ux and uy. And this is in the back way is when we use the ux and uy to compute the ud, which is the whole image gradient. And then we will have cal ux1y is when ux, uy, ud to compute ux1, uy1. And the last is the cal new, which is use the ux1, uy1, u0, u2, and lambda and t to compute the new u. And then we transfer the new u, which in the program we represent as u temp, but then we will transfer back to the u to start the next generation. Okay. Then this is the step we will transfer the u temp back to the u, which is u temp from the cuda malloc device to device. The denoising result is here, and the run command is here. And last, this is a reference, which I use the video of that.